the argand diagram. Now, as mentioned yesterday, we can't place complex numbers on the number line because the number line is for real numbers. And so all the imaginary numbers are above or below. It's like the flies hitting you in summer and things like that. They're actually imaginary numbers. So next time a fly attacks you, you know, oh, gosh, it didn't really happen because that was imaginary. Now, we can still get a picture. We can still place them on a diagram. The diagram is called the argand diagram. Now, interestingly, it looks very familiar. It looks just like the Cartesian number plane, which is quite convenient. So we can imagine our x-axis is our real axis. The y-axis becomes where we place the pure imaginary numbers. So where there's no real part. And then the others would go accordingly. But if we think the real value as x and the y value as y, it becomes a very simple case of plotting points, which will represent the different numbers. So if I wanted to plot the number 2, no big deal. We put it there at 2, same as we always have. But if I wanted minus 3i, that one would go on the imaginary axis at minus 3. But what happens if it's a mixture of real and imaginary? Minus 2 plus I, we just plot the point, minus 2, 1. 4 minus I, guess where we plot that? 4 minus 1. There's D. 4 plus I, where would that go? Now this brings up our first nice feature. What can you tell about D and E? They're conjugates. And so conjugates will always be reflections in the real axis. What about, watch this one, the point F. So I'm going to multiply by negative 1. It would become the point minus 4 plus I. Where shall I plot that? Yeah, there it is over there. You might think, oh yeah, big deal. But there actually is something quite cool about that as well. See? Minus 4 plus I, 4 minus I. So they're not conjugates, but they're sort of like opposites. So they rotate at 180 degrees. And that's it. There's D, which was plus 4 minus I. There's F, which was minus 4 plus I. They're directly put. So you could join them with a straight line going through the origin. How about this one? If I multiplied by I, 4 minus I, I get 1 plus 4i. Let's plot that one. And there it is up there. Multiplication by I then means rotation 90. Because think about it. We know I squared is negative 1. Right? So when we multiplied by I squared, we ended up rotating that point 180 degrees. So if I only rotate I, not I squared being I times I do half of it, 90 degrees. So multiplication by I will always rotate the point 90 degrees. Multiply by another I, so I'm now multiplying by minus 1, 90 degrees. And then I could do it, and so on. So every single complex number has a unique position on the argand diagram. There's only one complex number for each point. So let's have a look at this thing called locus. Horizontal and vertical lines. Okay, in Cartesian geometry, we'd know, well, that's y equals c. But if I'm talking about locus, imagine I'm plotting every possible complex number that I can, and I end up with this horizontal line, and we're saying, what do all these complex numbers have in common? Well, what they have in common is that their imaginary part is always c. So it's another way of naming our line, but if instead of thinking of it as a number plane, we're thinking of it as an argand diagram. Yes, it's the line y equals c, but in terms of complex numbers, it's the line, the imaginary part of z is always c. Because the imaginary part was y, so y equals c. And vertical lines, we can do a similar thing. Cartesian geometry would say, oh, well, that's x equals k. but when we're talking about complex numbers, it's the real part is always k. So every single point representing all those different complex numbers on that line would have the real part being k. Circles then. Remember we said z times its conjugate was always the sum of two squares, or x squared plus y squared. So if I've got a circle, centre at the origin, I know that has Cartesian equation of x squared plus y squared is the radius squared. But we just said x squared plus y squared is a complex number times its conjugate. So we can express this as z times z conjugate is equal to r squared. So that would be the locus of z in this case. So if I wanted to find and describe, what would that represent? Z plus 4 plus I times the conjugate of z plus 4 minus I is equal to 49. What are your thoughts? What do you reckon it is? Circle would be a good guess. Seeing we've just talked about two things so far, or three things. Vertical line, horizontal line, circle. I'm picking circle. Why am I picking circle? Because if I was to expand that whole thing out, at some point in there I'll have z times z conjugate. It's going to be a circle, but there's going to be some shift happening. The centre won't be at the origin. Where do you reckon the centre might be? 4 plus I? Minus 4 minus I? Let's see. If I did expand the whole thing out, okay, let's tidy it up a bit, just a bit if you're patient, and eventually subbing in x and y plus iy for z, eventually you could come down to this equation. So if you're ever unsure, you could just substitute in x plus iy for z. For its conjugate, you would substitute in x minus iy. So eventually I come down with a Cartesian equation, x squared plus y squared plus 8x plus 2y, and so on. Tidy that up a bit more. Still, well, we can see it is going to be a circle. Still don't quite know where the centre is, so let's keep going. It does factorise to be x plus 4 squared, y plus 1 squared is 49. So yeah, that centre is at minus 4 minus 1. So what does this tell me? I know the basic curve was z times its conjugate. All that's happening with this second one is that there's a shift happening. I've got z plus a complex number, and then in the second one I've got the conjugate of that same number. So the centre will always be what's with the z, not with the z conjugate. But remember, it's minus the centre. And so yes, our locus is a circle, minus 4 minus 1, and the radius would be 7. There we go. So z minus omega, and then the conjugate of z minus the conjugate of omega is going to be a circle, and the centre is at omega. Oh, whoa, what was this going to be then? Anyone want to have a guess on this? 1 on z plus 1 on z conjugate is equal to 1 without cheating and looking. What do you think this would be? A circle. Okay, we got two choices pretty much at this stage, line or a circle. So we're going for circle? Let us see. What am I going to do here? I'm going to multiply everything. I'm going to get rid of the fraction, basically. Get rid of the fraction, multiply everything by z times z conjugate. Oh, there's that thing again, z times z conjugate. So yes, a circle is a good guess. There we go. Z conjugate plus z is twice the real part. So I know that's 2x. Z times z conjugate is x squared plus y squared. Well, there's the algebra. You can see it quite easily now. Playing around with it, completing the square. Yes, indeed, we got our circle. So when you look at something and you're unsure, as I say, you can always substitute in x plus iy at any point and then work out from the Cartesian what it happens to be. Like this is a circle. There it is. Ooh, that would be a picture. See? Circle, centre 1 naught, radius 1. Oh, whoa. Remember, we're talking locus here. Excluding the point 0, 0. Why is it excluding the point 0, 0? Right. Remember, always go back to what the original thing said. And the original thing had Z on the bottom. So Z can't be the number 0, which when we're talking about real and imaginary is 0 real part, 0 imaginary part. So the point 0, 0 would not be included in this one. All right. We'll look at these sort of locus questions in a bit more detail later. The reality is there's actually an even easier way of describing them. But it involves using terms we haven't looked at yet. So once we see those terms, it'll be much easier than what this is.